Okay, so despite this rather technical title of my talk, I will also try to avoid all technicalities concerned with category theory, and in fact, this what is on the display here will appear only on the less transparency of my talk. So I would rather devote the whole talk to making the point which I want to raise and to solve. Not to solve, but to address in a sense during this. Okay, so from some point of view, this is an exercise. So how far you can go with, I would say, unified formulation of various theories, which is known for classical physics, classical mechanics, and quantum mechanics. Beyond that. And this is because, okay, it is nicer to have more examples, and then you can ask the question about how universal or how fruitful is such an approach. Okay. So let's start with classical versus quantum mechanics. So most of us here are physicists, so probably this is trivial for them, but for those who are not, I will try to summarize the similarities and differences. Okay, so in classical mechanics we have something, usually the description of classical system or classical mechanical system is made in terms of phase space, okay? So phase space, so there is, okay, without going into details, it is a manifold, differential manifold, with appropriate structures. Okay, so the structures which are important for such, I would say, canonical formulation of classical mechanics is Poisson or symplectic structure, and there is also some measure which allows us to calculate probabilities in a sense. Okay. So there are observables which are representing physical quantities, okay, or physical properties of a system, and these are functions on a phase space. And elementary observables, there will be a characteristic functions of subsets of this phase space. So in this simple statement, or it could be formulated in forms of questions, whether our system is in this particular subset or region of a phase space. Okay, so this is yes or not answer, and these are elementary observables. And states, there will be a probability distribution on measurable subsets of the phase space. So these questions would be about the probabilities rather than the and then the mean values of elementary observables are calculated from this probability distributions. Okay. Okay, so how it's in quantum mechanics. Okay, so observables are self-adjoint operators in some Hilbert space. Elementary observables are projections on closed subspace, so it more or less these are, when formulated in form of questions, it is a question whether the state vector, so in the case of pure state, okay, has a component in this particular closed subspace, and states in general are density operators, so are self-adjoint, trace class, non-negative, definite, normalized, trace normalized, I mean, in the Hilbert space. There is no clear notion of the phase space, and this will be my point during the rest of the talk. So, Okay, so to maybe not summarize, but to somehow highlight something, some differences and some similarities between these two theories. So we can ask, so what there is? Okay, so what are the ontologies of these both theories? So in classical mechanics, what is the most important is that values of observables are dependent on the actual state of a system, and in a sense are intrinsic properties of systems. They objectively exist. Okay? They're completely independent of whether we measure them or not. But on the other hand, probabilistic features, if they are relevant for the particular setting, and they usually are due to lack of precise knowledge of the actual state of a system. So this is, in principle, we can gain more information by refining our measurements. In quantum mechanics, it is opposite. We meet an opposite situation. So values of observables, which are also dependent on the actual state of the system, become determined by measurements performed on a system. They are not intrinsic properties of a system in this sense. Okay? So, on the other hand, probabilistic character of the theory is due to some intrinsic or ontic randomness of quantum mechanics. Okay, so taking into account, there is probably not much hope to unify these theories in one. Okay, and this will be the point of the further work. But before that, I want to introduce the no signaling theories, which were actually historically which were considered as some kind of an extension or not generalization, but some alternative to quantum mechanics, in the sense that they were constructed in order to answer the question, what are the minimal assumptions about, I would say, the outcome of experiments which would then determine uniquely quantum mechanical character of this of a system. Okay. So this is a, I would say, schematic view of the correlation experiment as seen by the theorist. Okay, so in a simple case, in the simplest case, we have two subsystems, and we feed the system with some okay states, okay, of the or maybe no, maybe better to say no. These are the part of the larger system, and on each of the subsystem we can measure something. Okay, so A and B are the observables in a sense. So in a sense we can try to measure or to determine the values of the physical quantities A and B on this in the subsystems. Okay. And we can perform such an experiments many times, say, and then we can encode the results in such a probabilities. This is a probability of obtaining the result alpha when A is measured, alpha and beta when A and B are measured on this, respectively, on the first and the second subsystem. Okay. So this P as a probability is positive, normalized, and no signaling. And no signaling means that actually there are well-defined such a marginal probability distribution, so which physically means that changing the input in one box so does not influence the outcomes on the other. So this is some kind of a caricature or a simplest version of causality. If it is not fulfilled, so the observer in one laboratory could get information about the choice of a measurement in the second one, even if no communication is possible. So-called paradigm of distant laboratories. Okay, so and what is interesting are actually the properties of these correlations. And as probably you know, for different theories, say for classical theory, such a quantity which is constructed out of these probabilities, of these conditional probabilities. In the simplest case, when we have two observables in each laboratory and two binary outputs, okay, so say plus and minus 1. So you can construct such a correlation, okay, or which I denote by S, which is the mean value of this kind, and then it's easy to see that since this is true according to this assumption, so this is always smaller than 4. So we can carry such a measurement scheme out classically or quantum mechanically. And in both cases, there are some further restrictions of this of this inequality. So the setting you usually take into account is the following. You have the decay of, say, for example, spin 0 particles and spin components measurements in direction given by vectors of these two products. So one is going here, the second here, and when they are far enough, we can measure, for example, the component of spin along the different directions. Okay, and then these outputs are indeed plus and minus 1, and okay, and in classical case, a state of a system is uniquely determined by values of some microscopic hidden variables. We are not able to determine their actual values, but know or guess their probability distribution. The result of measurements are averages over them. So we assume that when we measure, so there are some other, I would say, circumstances which determine this outputs, but this is the only uncertainty which we have. In any case, this is everything is calculated according to classical probability theory, and then, as you know, we obtain something like Bell inequality, that it must be smaller than 2. In quantum mechanics, we can consider, obviously, we can also obtain different values, but when we consider this particular input state, which is an entangled state, so and then perform this kind of calculation of mean values according to the rules of quantum mechanics. So we obtain the value of this S equal to 2 square of 2. and this is the maximal value, actually, which we can obtain quantum mechanically in this setting. This is so-called Zirelson bound, and yesterday Michał told us about that something more. Okay, and what we can do else, and then this is then comes this no signaling properties. So the only assumption which we have about these probabilities is that there are no signaling. So we can try to invent such a situation, such a, I would say, probability, conditional probabilities which fulfill this no signaling condition, and this is an example of so-called Popescu-Rorley no signaling boxes when this conditional probabilities of obtaining results alpha and beta. Once more, this is the same setting, so these are plus minus 1 of two observables A and B are given by this matrix. And then it is easy to check that if you calculate something like this, this is equal to 4. So you definitely saturate this maximal result of this S, maximal possible result of this S. Nothing more can be done. Okay, so first thing which is connected with this no signaling box is that obviously, so what does it mean that we have some probability distributions, okay? So as far as we know, there is nothing like non-signaling setting in actual, in this case, okay? So there are no Popescu-Rorley boxes in the real world. So first we have to justify that it is, okay, it has something with probability, okay? And then how to do it, okay? So first there is something which is a quantum logic approach, and I agree with Bob that this was rather a failure. Probably I don't know whether from the same reasons I will tell for which reasons it was a failure for me. But nevertheless, it could give some insight into the problems which appear in, say, unifying these three theories in one theory, having some common ontology, and I would say, and this will be the leitmotif of this one. Okay, so what are the elementary propositions? Let me recall again. In this case of quantum mechanics and classical mechanics and quantum mechanics, so first, in classical mechanics, does our system belong to a measurable subset of the phase space? In quantum mechanics, is the result of measuring the projection on a closed subspace of the Hilbert space of the system equal to 1, at least for pure states. For you can formulate this also for using density matrices for mixed states. And with these PR boxes, there is nothing more like does measuring A on a subsystem gives an outcome alpha. Okay, you do not have any other structure beyond that. So this is okay. So to say something about correlations, you have to have rules for combining or composing this question's proposition. For example, you have to have a possibility to pose the question: does measuring A on the first subsystem and B on the second one gives outcomes alpha and beta? Okay, so from this we can construct kind of lattice. Okay, so I will not use a precise formulation, but you can define so-called minimum and maximum of two such a proposition. Okay, of two A and B and negation, and then the whole propositional system is the partially ordered set, and it is partially ordered by implication. So you can impose this. So you can define this in terms of this joint and meets, joints and meets. Okay, and this is clear what I mean. So then there are implication, and this partially orders the sets, because if one sentence one statement implies the second, so there is a link between them. If not, there is no link, so the set is only partially ordered. Okay, there are some minimal and maximal elements usually in this formulation, so there is always false and always true. The result is the following. So the structure for classical mechanics is simply a Boolean algebra, and this reflects immediately the structure of this, I would say, subsets or measurable subsets of a phase space. Okay, so in quantum mechanics, it is something which is technically said orthomodular lattice, but this is simply the construction which comes from the fact that, as you remember, the elementary questions were about the projections on the closed subspace of the Hilbert space. In this formulation, these are simply subsets, because this is subspaces, because everything is finite dimensional. But so what does it mean that how to join by using by combining two I would say outcomes that are simultaneously, or maybe no, maybe better to say how to combine the questions whether A and B. So this is by I'm sorry. So this is by taking the intersection of two subspaces, and this is okay. This is like in classical mechanics. You can. This is also a subspace, but in the case sum of two subspaces is not a subspace, so you have to find the smallest. The smallest subspace which contains the sum, and this is the problem. Okay, so that's why it is no longer a orthomodular lattice. And what is the most important thing is that it's non-distributive. So the meets do not distribute over joints and vice versa. Okay, so what is in the case of this Popescu-Rohrlich boxes, this we were able to reconstruct just from the property of this correlation functions, and for some pathology is visible here, so that it depends a little bit whether we have two subsystems or more subsystems. These are technical terms. What are actually these structures? This kind of structures, but in cases they are also non-distributive. Okay, so first, why for me this approach from the point of view of quantum logic is not satisfactory. So the first thing is that for philosophical reasons, okay? So this is the quantum logic approach has rather epistemic flavor, so we simply concentrate of learning system from the properties, not what the system is, okay, or what really exists. But more important is that due to lack of distributivity, no signaling box logic, as well as logic of quantum mechanics, obviously, is hard to interpret as a truly logical structure. So this is for me the point, because P or Q is true doesn't mean that P is true or Q is true. For example, in quantum mechanics, this is a cat state. And there is no good, well-defined implication, okay, in this non-distributive structures. Okay, so this is why this is not satisfactory, and this is why we try to understand the approach by category theory, which obviously which as probably you know for quantum mechanics was elaborated starting from the papers of Isham, I think, and to apply this to our they are not our, but to Popescu rolling boxes. Okay, and then this is also the hope that there will be some common ontology. Okay, so there will be some common structure which I can say that is behind all these theories, and then that would somehow say me that I am saying that my questions are about something, okay, and not only about the values of some measurements. Okay, so Schrödinger was cited several times here, I think. So this time I will cite Niels Bohr, which pointed in his, I would say, defense, or maybe arguments for something which he called, which is the somehow principle of correspondence. Nobody knows what does it really mean, in fact, but at least it can be read out from this citation. I will not read it aloud. Everybody can read it now. I will keep it for a moment. But the main idea is the following, which was also mentioned here, I think, by Professor Heller, that we are somehow constructed and evolved in a way in which we perceive our environment through classical notions. Okay? So, and this is the main idea also of Bohr in these three citations, three passages here. So that that all what is what we can learn from quantum mechanics, we have to explain this or express this in terms of classical terms. So obviously he didn't mean what I mean here, that we should somehow construct all these theories to be as analogous as possible to classical physics. Okay? So our goal is to restore the ontology for the quantum and no signaling theories. And how to do, what is this I would say, goal? So find a well-behaved phase space for quantum non-signaling, or especially for no signaling system. For quantum, it was done in a sense. I will show you. Find a logical structure of the set of propositions and reproduce the probabilistic properties of the theory. And to fulfill this as well as I would say, to be as close to what Bohr requested or from us, so this should be, as I told, as close as possible to the classical structure, okay? And also the logical structure of the set of propositions should be as close as possible to the classical one, okay? So, how it was done for quantum mechanics. So to be very short and non-technical, so what is most important in quantum mechanics from this point of view is that observables do not commute. Okay? But we can also always find a set of compatible measurements or compatible observables. These are those that commute. Okay? So, and this defines so-called context. Okay? So this is the set. This is this commuting subalgebra of observables. Yes, and as it is here written, this context has a well-defined physical meaning as a set of compatible measurements. This set of contexts is a category. It can be treated as a category when these commuting subalgebras are objects and arrows are defined by inclusion. Okay. Obviously, this is also a partially ordered set. And now it's a little bit technical. So using this category, we construct an appropriate topos. Okay? And topos is something which is as close as possible to something which we can say a set. Okay, and this are the family of sets. Okay, in the sense that it has many important properties. Okay, so propositions are sub-objects. So there are some sub-objects of a set are subsets. Okay, so these are analogous construction in the topos. And in the set of subsets, as I already mentioned several times, the underlying logical structure is the Boolean algebra, which corresponds to intersection and set theoretical sum of subsets. Okay, and here this is the Hating algebra, okay? So which defines some intuitionistic logic, and this is okay. So you can think about some kind of this logic if you consider not a set of subsets of all subsets, but for a set of closed sets, closed subsets of a set. Okay. So intersection of two closed subsets is okay, and so, but the and some also, but the even but there is, but if you want to make the negation completion of this subset, it is not a closed subset, so you have to close it, and that makes this algebra no longer Boolean. Okay, and this is maybe not so untypical even in the classical mechanics when you when you are confronted with some kind of unsharpness of measurements. Okay, you are not sure what happens at the border. Okay, and so our input was an attempt to do it in a case of no signaling boxes. So the main problem is here that there is lack of this structure which somehow allowed for construction of this topos or to consider this compatible measurement as a commuting subalgebras, but nevertheless it is possible here to consistently define context. So the situation where this situations where the measurements are compatible just upon analyzing this probabilities, this conditional probabilities. Okay, and the following construction with some non-important technical details could be repeated here. So here we can do more or less the same with the same result. Okay, so we can obtain, I would say, ontology of the system as a topos. Okay, so this phase space here is also a kind of topos. Okay, so let me summarize. So in terms of category theory, we can restore the ontology of non-classical theories. So in this, so I put it in the quotation mark because, okay, so restoring the ontology is maybe too much to say that this is restoring the ontology, but we can find appropriate phase spaces, okay? And the logic of propositions becomes distributive, so there are no problems with this non-distributivity which I pointed before, but at the price of the absence of the law of excluded middle. And what is our result that is possible not only for quantum mechanics but also for no signaling theory. So this suggests a question about universality of the whole procedure. So whether it could be applied also in some other cases. What cases I have in mind? Okay. So first you can try to approximate quantum mechanics by an appropriate sequence of no signaling theories. Why it is interesting? We are able to prove that for this Popescu-Rohrlich boxes, formally the Heisenberg uncertainty relations are not fulfilled. So in a sense, they are more similar to classical theory than to quantum theory. So if you can, I would say, approach quantum mechanics from above, so from this extreme non-signaling boxes like Popescu-Rohrlich, going some sequence to the quantum mechanics. So it would be interesting when this Heisenberg uncertainty relations reappear, so which could also shed some light on these relations themselves. Okay, and I don't know how to do it from the other side, but nevertheless, this is something which I find quite interesting because it seems that quantum mechanics is distinguished out of these theories by the fact that really the Heisenberg uncertainty are important here. Okay, and this was my last transparency, and these are the most important papers we wrote about that, and bold faces are the names of the real working persons. Okay, so work horses for that.